The Earth orbits the Sun at a distance of around 93 million miles. The furthest planet, Neptune, orbits at around 2.8 billion miles. Our home galaxy is far larger, containing more than 100 billion stars and planets. Current estimates place it at around 100,000 light-years across, making it around 200 million times larger than the radius of Neptune's orbit. But the furthest object we have ever detected is much, much further, at a distance of 33.8 billion light-years away. So, how is this even possible? How do we know how far away our neighboring stars are? Or distant galaxies, billions of light-years away? Consider a set of cubes. Each is at a varying distance from you. When you move side to side, the closest cube moves the most and the furthest cube moves the least. So there must be a relationship between the distance of the object and by how much its position appears to change. The same principle applies to stars. When the Earth orbits around the Sun, the position of the observed star will appear to move. The closer the star is, the more the perceived image will move, and the further the star is, the less it will move. This is stellar parallax. But for this to be useful, a singular star is not enough. Instead, we need to compare its movement to something else. Considering the set of cubes again. If everything else were removed and only a singular cube remained, you can't actually tell it's moving anymore. It just looks stationary if nothing else is around. So we need a still object like this plane to compare it to. But what can we use for a star? It turns out that there is a natural background to compare the nearby star to, distant stars, since if they are far enough, their movement will be extremely small compared to the movement of the closer star. With that, it's time to finally calculate the star's distance. Due to the natural movement of the Earth, every 6 months, there's a significant change in the apparent position of the star. At each of these 2 points, we take a photo. Now, between these 2 images, the amount of pixels by which the position has shifted is proportional to this angle. But to find out the exact angle, the device usually has a plate scale, which is basically a ratio between the pixels and the angle. Now we can use simple trigonometry with this right-angle triangle to get this equation. But given how far away the star usually is, by using the small-angle approximation, we get this final equation. Now, this is a great method to use, but a major issue is already clear. What about the distant stars? What if I want to know how far away these stars in the background are? Stellar parallax simply isn't useful for extremely large distances. Instead, we need another method. When a candle burns, it produces light. As you move away, that light gets fainter and fainter, even though the brightness of the flame being produced remains the same. This suggests a correlation between the distance of the viewer from the light source and the perceived brightness of the light source, which naturally can help with stars. So, to start, what is that correlation? First, let's define what brightness actually is. In physics terms, it's usually described by intensity or flux, which is the power transferred in the given area. So, at a given point, the intensity of the light is the power it's receiving divided by its area. Now, let's define power. In the context of the light produced by a star, the power is the total amount of electromagnetic energy emitted per unit time. This is called luminosity. As for the area covered by this energy, typical stars emit energy in all directions equally. So, the energy is emitted over a spherical surface area, which has the equation 4 pi r squared, where r is the distance of the viewer. Therefore, the final equation for a star's light intensity is given by this. But, for an astronomical object, this formula isn't enough by itself. We can measure the intensity felt on Earth, but how are you meant to know how much power an object billions of miles away actually produces? Well, it turns out that certain cosmic bodies have a predictable luminosity regardless of where they are. Then, if we know their luminosity and measure its intensity on Earth, we can calculate its distance by rearranging the equation from earlier. These are called standard candles. So, If a galaxy, a nebula, or some other body contains a standard candle, we can find a distance to that body too. At this point, it's natural to ask the question of how we found out their luminosity in the first place. How did we find out specific types of objects share a luminosity? Well, if the object is nearby, we can apply stellar parallax to find out its distance. After measuring the intensity of its light felt on Earth, we can rearrange the equation earlier again to determine its intrinsic luminosity. And once this is tested on enough examples, we can establish that certain objects have predictable luminosities. That might be supernovae exploding with a consistent brightness, or Cepheid variables, which are stars pulsating with a time period proportional to its luminosity. So once we measure its time period, we can find its luminosity. Now, this extends our ability to calculate distances even more. But this is still not enough. With objects billions of light years away, their light is just too faint on Earth. So it's time to use another method, one which extends to the edges of the observable universe. Everything in the universe is moving away from each other, slowly drifting further and further into the dark. Except it's not matter moving away from each other, but the space between them. The universe itself is expanding. But how is this important for finding cosmic distances? Let's start with two simple observations. When we look at extremely distant galaxies, something is different about the spectrum of light it's emitting. It's more red than it should be. Or more accurately, their wavelengths have increased compared to what we'd expect it to be. In addition to that, the more distant the galaxy, the more prominent this effect is. So how do we explain these two phenomena? To start, we know that the space in the universe is expanding. When light passes through that space to reach us, that light is stretched as well, increasing its wavelength. This is what leads to redshift. Now, for more distant galaxies, the space between us is larger. And if space itself is expanding, then there is more space to expand for a more distant galaxy, so light must also be stretched more. Now, since redshift increases with distance, there must be some sort of relationship. But to derive it, first we go back to standard candles. By using them, we can find a distance to a particular galaxy. Then, by measuring the redshift of that galaxy, which is defined as the ratio of the difference in wavelength to the original wavelength, we can plot a graph of redshift against distance. This turns out to be a linear relationship. So, when we measure the redshift of a faraway galaxy, we can correlate that back to its distance. However, for high values of redshift, this linear relationship breaks down. At low redshift, the linear relationship is proven from approximations incorrect at large values. This here, Hubble's constant, is exactly equal to the rate of expansion of the universe, except we know that the rate of expansion of the universe has changed over time. For closer galaxies with low redshift, this isn't a problem, since the time for which they have drifted for is extremely small compared to the age of the universe, so the rate of expansion is more or less constant. But for high redshift galaxies, they existed during changing rates of expansion, so we can't make the same assumption. The replacement is the Hubble parameter, a function of redshift. If you're wondering why it's a function of redshift instead of time, think of redshift as analogous to it, since the longer something drifts for, the stronger the redshift is. Now, to link it to distance, consider that the reciprocal of rate is time. We also know the distance traveled by the light from a distant galaxy is speed of light multiplied by the time taken. Then, if we add each piece of time the light has been traveling for during different values of the Hubble parameter, we get the total travel time. This can be expressed with an integral, giving us the final equation. Throughout this video, you might have noticed each method was needed for the next. Parallax was needed to calibrate standard candles, and standard candles were needed to find the relationship between redshift and distance. So we often call this sequence of methods the cosmic distance ladder, each technique building to further distances. And according to our current knowledge, this is the highest level.